Right, so thanks Arjun, and thanks to the organizer for inviting me to this workshop to get this presentation. Again, I'd like to talk today about our team of heterogeneous robots that we developed at the Institute over several years, and how we demonstrate their capabilities as well as their mapping and SLAM capabilities in an analog demonstration mission that we executed in Sicily on an active volcano. So I'd like to start this presentation by showing this image that I think nicely illustrates our vision and our strategy for mobile robotics exploration. So we believe that systems are, well, I mean, they are already, and they've shown already to be a precursors of human activity in space. And we believe there will be anyway an extensions of the capability of the astronauts while operating on a planetary soil. So they have to be able to execute several tasks, starting from scientific tasks, as well as deploying instrumentation and fixing and building up infrastructure. To do that, they will definitely benefit from heterogeneity, so heterogeneous aspects, and the capabilities of operating in a team. That of course will also put some challenges because of so adding this modularity, handling the the organization of the team and the communication for the team and so on. And that's where we head, let's say, towards. So I'd like to contextualize a bit what we do in a context of an overview of project that we have been developing. So it all starts with a project called Robotics that started in 2012 and in 2017. Where we first started to develop technologies to allow accessing very inaccessible terrains from mobile explorers. This was a project as a result of a Helmholtz Alliance, so an alliance of Helmholtz institutes, where we focused on the space domain, even though also marine domain was involved through other partners, and it culminated in a demonstration mission in 2017 by means of one of our mobile robotics system, the lightweight rover unit, and a lander on a soil on Mount Etna, which is a volcano in southern Italy, in Sicily. And here we had to demonstrate the capabilities of the system to deploy an array of seismographs through handling these boxes that he had to grasp, pick from the landing site, and then store in the environment. And then this leads to the project that is the topic of this talk, which is Project ARCHES, which was again a Helmholtz Alliance project as well, but with more partners now, and also the participation of the European Space Agency through the Human-Robot Interaction Lab. Here we took the experience of Robotics, and we wanted to implement more capabilities to the system, as well as involve more systems in the loop. So while we started with one system with Project Robotics, now we have three different systems that have to collaborate together with different capabilities for performing measurements and deploying instrumentation. In this case, there were much more complex tasks and sequences of tasks and hierarchies of tasks. And we had a remote operations center to check the execution of the whole mission. Just for some PR and to contextualize a bit what we do, we started off also with a field robotics branch for performing applied research at our institute. In this case, I just want to show and mention this project that we did in collaboration with the World Food Program, which in collaboration, so with them, we equipped a vehicle, which is a Sharp, one of these amphibious vehicles, fully mechanical, that is used by the World Food Program to do last mile deliveries in the contexts of war, for instance, in South Sudan. And here we wanted to enable this vehicle to be teleoperated. And to do that, we had to take a lot of experience from developing navigation systems from our robotics systems and putting that into this big vehicle. So you see here some examples of perception for traversability estimation and local mapping. As well as some, here we have cameras for teleoperation and so on. And then the results of ARCHES, so again, the topic of our talk, but just to show, we would then use in the context of these project called iFoodies to deploy to an agricultural setting, where we want to monitor the flow of pollutants in water in agricultural domain with a use case in northern Germany. And here we will actually do for the first time at our institute, extend our network of systems to incorporate live also feedback from a team of robots operating in the underwater domain. And then all the research that we do with a lot of claims to be then eventually, have application in actual space, in a space domain. We were very happy that in 2018, Project MMX, in the context of the MMX mission, so JAXA's Mars Moon Exploration mission, we had the chance of developing these systems. So it's a tiny rover built in collaboration with CNES, where we took a lot of experience in developing navigation systems again for our systems, so from state estimation to local mapping and path planning, and then put them into an actual planetary rover. So we had in this case to redesign a lot of, let's say rewrite a lot of the code that we implemented already to do state estimation into a form that is executable on a very tiny architecture which is space qualified. And to put in this rover that which has the goal of navigating into the surface of Phobos, which is one of the 2 moons of Mars, which is a very extreme environment to navigate because of the milli-gravity conditions, but also because the conditions of the surface are almost totally unknown to the very fine scale that is really relevant for the actual robotics navigation. And just to show here some components and some snapshots from the navigation system, where we take stereo images, do semi-global matching, visual odometry, pose estimation. This is all software that has been distillated from the ones that run on our systems, and that we'll talk about, and then put into, again, a space-qualified hardware. Okay, let's now go to the ARCHES analog mission, which is the topic of our talk, and starting with an image of our mobile systems that we developed at the Institute. The mission had basically the goal to develop technologies and methods to let autonomous system operate into very highly inaccessible terrains, again in two domains, so the space and the marine domain, and again we focused on the space domain. Of course, here we wanted to let more robots act together, and therefore we had to develop a new methods for robot interaction. And to manage the whole mission, which was again resulting as a complex of, a set of very complex hierarchical tasks. And we wanted to then test all of that into through a field campaign on a relevant analog environment, because that then had the goal of raising the TRL of our technologies that we demonstrated. So the mission eventually was a 4-week field campaign close to the top of this mountain, and where it culminated into 3 days of actual demonstration. And these 3 days, the first day was a day where we wanted to demonstrate the capabilities of our system to perform scientific tasks. So we want them to be able to basically navigate to spots of where something of scientific interest was laying, and being able to perform observation and sampling. The second day was instead dedicated to ESA and the topic of teleoperation. So there they operated the Interact rover, which is a robot that has been already operated by the International Space Station from Luca Parmitano, one of the astronauts. And here DLR astronaut had to sit on in our mobile operation center, remote operation center, and from there with a specific joysticks with force feedback, it had to basically operate the system to do it in both navigation to pick some samples, and then remote manipulation, which was fully teleoperated. And the positions of these samples to be teleoperated was then parsed by the positions scattered by our systems in the previous day. And then the final day of demonstration was actually to show the capabilities of deploying infrastructure. So in this case, we wanted to demonstrate the use case of deploying a low-frequency radio array. So basically a stack of antennas that built up a radio telescope, where the scientific goal was to perform an analog mission to a deployment of an actual radio array on the far side of the moon, because of the relevant conditions to observe the activity of Jupiter. Okay, then let's talk a bit about our agents. So these are all the systems that we developed in the last 10 years at the Institute, and then we deployed it all together to perform some collaborative tasks. And these, so we start with the LRUs. So these are the lightweight rover units, are 2 robots with the same body and locomotion subsystem, as well as navigation subsystem, because they use a stereo vision and inertial measurements. The lightweight rover 1 is specialized to be an observer. So it is specialized to perform scientific tasks. So it has a big pan tilt head with 2 cameras at the side, which are scientific cameras. So they are normal cameras without IR filter and with a filter-bearing wheel on top. So basically, they can choose which wavelengths to filter out, and by doing so, it can segment landscapes based on their mineralogical components, which is quite cool. And then it had a thermal camera and a narrow-angle camera, so just a camera with a tele lens to do, for instance, observation of our other team in the system, which is our drone. And also, it operated as a remote landing platform for our drone, which I'm talking about later. And then we have the other system, which is called, again, it's another lightweight rover unit. We call it a LRU2. Again, shares the same platform, but this time it is specialized to interact with the environment. So while the first one is designed to observe, the other one is designed to pick and sample and interact. It's basically the same system with a manipulator arm, which is a Kinova lightweight arm, but we developed a specific interface to it so that it can transfer data and power to and from the system, and also can grasp and attach to, so with a common interface to a different set of tools. Then we have our lander that we also deployed. I mean, we consider it as part of our mobile robotic team, even though it's not mobile, it's static and quite heavily, we'll say. Though it relays a communication to the systems, and it provides charging capabilities for the batteries of them. And it also acted as the system of reference for the operations of the whole robotic team, and it was also the reference for our SLAM system that then gave localization at all the time to, to all the team involved in it. And then we have our drone. So the drone is called Ardea. Is again fully designed in-house from the locomotion subsystem to the perception. It is a hexacopter in a Y6 configuration, so it's basically a triangle with counter-rotating propellers. It has a very specific vision system because it has a very wide-angle vision system in the vertical direction, so that it can fly under low ceilings, for instance, and in very narrow spots. And it shares the same state estimation and SLAM package that runs on the other systems, so on the mobile systems, so that they can, again, perform collaborative SLAM all together. Regarding the tools that the systems use, which are definitely part of the mission, big components of these missions, are these specializations of what we call payload boxes. So these are a common infrastructure to hold not only instrumentations but also samples. The advantage of this design is that they can basically be attached and grasped by our mobile manipulation system. And be deployed wherever needed. So they could be specialized, for instance, as a sample box container to put, bring samples back to the lander, but also as these antennas that then we deployed the last days, as well as Wi-Fi repeaters or power boxes for the antennas, and it was also specialized into a laser-induced breakdown spectroscopy instrument. The LRU2 then used a shovel as one of the tools. So basically it was this shovel designed in-house. I mean, nothing particularly special, but it could be grasped autonomously by the systems from this tool arsenal, basically. And it could just sample through rehearsed tasks, and then send back to some of these spots into the payload boxes. And then we used a hand, which was developed at the Kato Institute of Technology, which again was an exchangeable tool as well as the shovel, and then place them back in the rover. And when needed, when instructed, it would just grab the hand and then go and sample stones. And here you can see also some where here's tasks where he could go and grasp stones of relatively unknown shape, and then place them back into some of these spots in their sample boxes. And then the other parts of these, some other parts of the GO1, so the first mission, then we demonstrate the deployment and the usage of a LIBS instrument. So an actual laser-induced breakdown spectroscopy instrument, all casted into one of these boxes, and where the rover basically went far from us. We had to stay at least 50 meters away from the system because for safety, and it was just shooting laser at some of the stones indicated by our scientist team. Right, in terms of skills that then the robot could perform, we could monitor them and instruct them what to do from our remote operation system base. So the system could do, again, shoveling, and we could instruct it to shovel specific spots that were observable by its back camera. So this is images seen by the cameras placed in the back of the body. And then we could click, so the astronaut actually could click on some spots there, and then the system would shovel there and then place back. Same to aid the sampling, so the stone sampling skills. We used a deep learning architecture called Instar that we developed in-house, and here's the reference, which used stereo images to automatically segment unknown objects from the scenes. And this was extremely helpful because then we could show some false color images to the user, which could then click on top of one of those stones. And then the rover would actually approach it with a reasonable approach configuration and then actually grasp it and then place them back with quite a lot of tolerance in the position then. And then, of course, the DLR-U1 had these big, with these big science cameras, we could instruct the rover to use which filter to use, and then to acquire panorama scans wherever needed. So this is an image of the spots where we deployed our system. So this is a plateau near the top of Mount Etna, which is this active stratovolcano in southern Italy, in Sicily. And here we can see both the landing site here in the center of the image, where we deployed 4 big containers to do local operation of the robotic system, as well as handle networking, communication, and of course launch. Here you can see there the top of the mountain in the southeast crater, which was always active for the whole month of the mission. And the landing site for the systems that we deployed, where we deployed the lander, was basically down here in the slope out of this image, so about 500 meters away and 100 meters lower. Here I will just skip. So the other big part of the mission was the remote operations center, which was actually down at the sea level, close to Catania, which was remotely located at a 20-kilometer distance, basically, where we though had line of sight to the actual landing site of the robot. So from them, we had actually full communication with the landing site, and the communication was set up like that. So from our container, we had 2 directional antennas. One was going to the lander, which was then relaying communication through Wi-Fi to the robotic systems, so the team of robots that was operating nearby. But then one of the other directional antennas was directed at the roof of the hotel where we were staying, at 20 kilometers about, something like that. And then there we set up a whole room with workstations. And there we had the same local network that was also running where also the robot systems were actually belonging to. So we would have, in simple terms, the same ROS network from the workstation in the hotel as well as in the robots. And from there we did all the remote operations and the mission architecture. Then I want to talk a little bit about the SLAM system that is implemented in the rover. Apart from the research aspects of it, the SLAM was a necessary and very important component for the whole mission operation, because it was giving the location of all the systems involved in the SLAM with respect to the lander, and this was giving then knowledge to the operators where the robots were at the time, and giving the best estimate of where the robots were located at the same time for operation. Of course, we assumed that GNSS was totally unavailable, even though we had it, but we wanted to, of course, simulate an environment where in the early stages of planetary exploration we don't have global localization. So our SLAM architecture that we developed fully in-house is a fully decentralized multi-robot and multi-session SLAM architecture, where all the systems involved in the group perform their own solution of the whole SLAM system, and they hold all the data needed to do it. So from everything that puts constraints in the SLAM graph, as well as all the local maps that then build up the whole map of the full session. And this is related to the need of having a very robust system. So we didn't want that one of the systems could be a single point of failure, and so each and every one of these systems could die at any moment in time, and the other ones could continue operating, and that would continue giving the remote operations center knowledge where the systems were. So the system is it's built in the sub-map paradigm, Basically, the system performs state estimation using visual and inertial measurements, and they all refer their measurements with respect to frame of references, where they know their local position and covariance. And once the covariance grows a bit too high, then they switch to a different reference, and so on. And all these reference switches then define the origin of submaps that then we, where also, rigid point clouds belong to, then we stack together. And these submap origins are the actual variables that are optimized in the SLAM graph, which is built not only by those, but also from camera positions related to the extraction of visual keyframes, as well as robot detections, and so on. And the system joined their SLAM graph together and to build up the full configuration by observing each other, so through April tag detections, or by performing place recognition through, well, fairly standard visual loop closure detections through binary features. Everything that the system creates, so all the constraints that they create and all the maps that they create, are all cached to disk and labeled by a session index, so that both operators can request to build up something that was captured beforehand, so the previous days or so, but also they can share missing pieces of their whole SLAM solution to the other systems if requested by them. So in case a communication dropout happens or any kind of data loss and so on. So we had a whole mechanism of data distribution. This is the topology of our SLAM graph. So where all these S's basically are origins of these submaps, and then all that the robot perform and do is are pose variables, which are referred to the closest submap origin, because to that we know an actual covariance for all the measurements, and so we can assume that the solution would be best anyway. In terms of place recognition, so the robot perform, of course, place recognition as we said. So they do both map matching based on 3D data if we prior on their poses is available, but also they do keyframe matching based on, again, visual loop closure detection through a vocabulary-less approach and binary features, so that they can establish constraints between robots which did not see each other again, so there's no prior between them, as well as sessions which were created in the past. And this is just an example of some multi-session testing of our of the SLAM system in our mobile robotics lab. So we have an outdoor lab at our institute, which is pretty big, and it simulates a lunar environment and a Mars environment. So where we have a big crater and some stones deployed here and there, which offers also some challenging conditions for perceptions, because the environment is fully unstructured, and that replicates what then we are expecting to see in relevant planetary contexts. And here we can see how we could match different sessions created in different times during a week about using mostly visual information. Then just wanted to mention some of the challenges that, of course, we encounter all the time when performing SLAM into these kind of environments, which is mostly due to place recognition. These environments are, of course, fully unstructured, and there is no, tracks of, human presence on it, and that means that the environments exhibit big perceptual aliasing. So images captured at very different places all look the same, but also at the same time there are no features that unambiguously define a single environment. And so the robot is having a very hard, time in trying to perform matches and then doing loop closure detection. And also the problem is that the system can navigate into this environment without any constraints in the path that they take. So of course the chances of intersecting viewpoints and having very similar images from what has been observed in the past is really, the chances are really, really slim. Just to give some visual examples though, here we have some videos of query and targets for some place recognition test that we did. And in the bottom here is a sequence from one of the actual demo days in the mountain, where one of the robots was actually looping around the lander all over and over again. So actually traversing an environment which is very close between, so the poses were very, very close to some potential, matches, but we could not get a single one because, again, viewpoints were not exactly the same, and there were no really unambiguous features, telling what is what. And also, other challenges, lighting conditions. The robot was seeing it himself over and over again, and many times we happened that the system was, validating keyframe matching between itself, and that leads also us to understand that, okay, we need some higher level understanding of what we are seeing to be able to efficiently operate in these kind of environments. Then, big components of the whole mission was again mission control and mission management. And we had this infrastructure where we foreseen the scientist in the loop to be able to operate the mission by giving relevant tasks and points of interest to reach. So we had during the demo some set of points where the robot had to go and operate, and then all of them were put into a planning tool. That was giving us a sequence of steps of operations that when they were then approved and then loaded from our remote operations center to the systems. And then when the system received all this information, they had to start planning their task in a different level of granularity. And to do that, something that was extremely important for the whole mission was our this tool that we developed in-house, which is called RAFCON. It is a hierarchical task state machine tool where we can define tasks in very different levels of hierarchies. And this is open source. Everybody can use it, and I encourage to do that if you work in the same field, because this was extremely beneficial. And then all the systems had a representation of a world model, which was then again really necessary, where especially for manipulation operation, but then was extremely useful for all perception operations, because they had a higher level understanding of and labeling of all the components that were joined basically in the mission. So basically, not only their position with respect to each other that was informed by the SLAM, but also positions of tools and boxes that were deployed in the environment. And this was necessary also to the SLAM system, because we use these boxes as artificial landmarks. But then we wanted to know if one of these boxes moved, or if one of these boxes was in the process of being manipulated, because then we could avoid using it to do that, because we didn't tackle dynamic scenes. These mechanism of synchronizing all the time the knowledge of the world by all these systems were a crucial task for the mission execution. Okay, let's now go to some of the results of this field campaign. So regarding the first mission, so this GEO-1 mission, we executed this mission in the first day. And into this first day, we had our systems up for 6-7 hours continuously operating, and to actually execute the mission tasks, it took around 3 hours and a half. And here the robots basically went through 9 different spots, of which 3 were reached by the LRU-1 to capture panoramic images with their science cam, and the other 6 spots were reached by the LRU-2 to be able to deploy boxes, as well as this time to take samples from the shovel and the hands and place them back in boxes, and then bring the boxes back to the lander, and so on, as well as shoot lasers onto 3 of these stones. I just wanted to mention that for these missions, we had our SLAM system executing continuously for more than 3 hours without any hiccups, and without loading the system computationally, and without getting into unstable situations. And that was due to, again, some design choices that we made for robustness. The system didn't move that much, so they moved for 300 and 200 meters each, mapping an area not really huge, but again, there was a lot of standing time, a lot of moving to fix the locations of these to reach these places and so on, changing batteries. There was a lot happening anyway. This is just an example I wanted to show of the octomap and the topology of our SLAM graph. This was actually recording during the mission, just a screencast. And here is just these transformations. Here are LRU-1, which is approaching the landing site again after going there and rehearsing. This was before the day before the first mission, actually, with some rehearsal. And these ellipsoids here you see here are the origins of these sum-ups with their covariances. And what is cool to see here is that as the lander was fully geolocalized, so of course, we didn't use the GPS, global pose information, but the lander was anyway fully geolocalized, so we needed, we knew 3D, the global location and attitude with respect to an in-frame. And so we could also overlay to the results of the SLAM maps also a DTM, so a digital elevation model built as a ground truth from remote observation. And then we can see how the octomap here built envelopes quite nicely the area in the surface in the DTM. And also here, zooming out, we see the boundaries of our crater that we were operating against. And then we also winched one of the rovers back into that crater. That was pretty cool. And one of the other craters about 200 meters above the landing site here. Right, and then with respect to the LOFAR mission, so the second part of our, let's say, relevant mission, here we had to deploy, so the goal was to deploy an array like that. So basically an array of box stacks, where the bottom one was a battery box and the top one was an antenna, fully functioning antenna. And all of these antennas were networked together and then could localize together to know, the best estimates of the geometry of these array, and then was actually used in the night of the mission to do some observations. During our demonstration, though, we could only demonstrate deployment of the first antenna there. Which anyway took 3 hours, and then we had other events to do and so on, but we were happy that we could successfully deploy one of these stacks where the robot had to approach the stack back and then had to place the top box on top of the bottom one with tolerated error of maximum 2 centimeters. Where we also had, of course, to account for localization issues, and there the robot had to, anyway, he went back to the box, to the first box that he stacked, and then he located the box using the cameras, and then he approached the box and then stacked the second one on top of it. So that was pretty cool. And the other system, though, that was not acting physically on the setting, though, was navigating all over the place and seeing these boxes that were again used in the SLAM context, and then fixing all the time the position of them with higher accuracy. So we checked a bit the accuracy in estimating the elevation of the terrain by just looking at some elevation maps that the rover built during these 2 missions, and we were quite happy to see that the accuracy was pretty good. We could reconstruct the elevation of the terrain in the landing site with median errors ranging from 10 to 20 centimeters. That was reasonably good for the scientific goal we had. And also in terms of localization errors. So this is the result of SLAM for the LOFAR mission, so this second one. And so LRU2, so the red line there that was going back and forth from the lander because it had to go there, get one of the new boxes, stack the box, go back, get the second one, go back again. So it was moving in a straight line, and then it had very low localization errors. That was perfect, good enough for localizing the box or previously deployed. And the second one, which again was moving way all over the place, had some, higher position errors, but still perfectly reasonable in the mission context. Okay, also in terms of computational load, the result of the design of having a very sparse SLAM graph then also allowed us to not overload the system on these 3 hours long SLAM sessions. The higher computational times are due to processing of these submaps that then were happening once in a while, once in, 10 minutes, 20 minutes, depending how fast the robot was moving. But we were very happy to not bottleneck the whole system where, not just the SLAM had to work, but 50 other components to do all the rest of the goals, perception, navigation, all the scientific goals, the knowledge, handling the knowledge base, state machines, and so on. And this is also just a very short example of a multi-session SLAM execution by using all the data that we recorded during the mission. Of course, they are all SLAM-centric, and all these yellow line then actually points to from the robots to the lander at the time of detection, and they were mainly driven by robot detections because, again, visual aliasing extremely high, lack of unambiguous features to observe and closed loops, and also we try to move the systems in a let's say star shape all away from the center, because we wanted to see and map a lot of different places in the environments. And so there was a fairly low, let's say, revisiting of the same places. So in conclusion, related to this mission, we could successfully execute our mission plans that we set beforehand. We could demonstrate collaborative behavior between our two rover systems and collaborative mapping between our systems and the drone. All these tasks were performed in partial autonomy by first instructions from the scientists, and then managing the execution of these tasks autonomously from the system. And I mean, the choice of developing components for robustness actually paid off, because with all single point failures that could happen during our mission execution, we saw a very few or none, and with especially with what regards SLAM, basically none. Yeah, I mean, we were very happy about that. However, we saw also a lot of areas to improve. So especially we saw that so robot detections that were very crucial to get good alignment between the maps of the different systems, as well as the relative location to perform collaborative tasks, was only possible through getting very close to the other systems, because we had to basically observe some small lateral tasks. And this is a big limitation. We want to see more in the future how to use high-level understanding to be able to establish 60 correspondences to systems at very larger distances. And also local navigation would benefit from high-level understanding of how the objective looks like. So instead of driving towards just with some metrics and counting the meters to the object of navigation, some visual surveying where we recognize the appearance of an object at very different level of details where we approach it, and then also overcoming occlusions. For instance, if we have a hill in the meantime, and then we go up, and then we reobserve the object again and say, okay, that's our target for navigation. And of course, it is very different for driving towards actual objects that stands out of the environment, or just areas. So we want to be able to use high-level knowledge to do that. And of course, testing. I mean, during the mission, we fixed a lot of problems that we had in our navigation stack, just because we could not replicate the same conditions in our lab. This is just basically tells us how precious are field tests in this case. So stepping ahead, what we want to do and in the next in the near future is address multimodality. So far we always use visual information because of the claim to be easily space qualified technology, of course, which is already used, and there's a lot of heritage, and we also had a lot of heritage. But then with all the advances in LiDAR technology, especially solid-state LiDARs, we can get closer to claims for space usage, and we want to address that. But most importantly, what we want to tackle is semantic understanding of the scene. So we see that traditional approaches for both mapping, SLAM, as well as navigation would really benefit from having different modalities for understanding what's in front of the systems, and semantics is one of those. So something that we are doing already is some semantic mapping and place recognition, but what we want to do in the future, possibly in the nearest future, is actually using more the knowledge base that we are anyway using for the systems, especially for manipulation tasks, but giving more attributes, more semantically informed attributes on the how the scene is set, so that the systems and the operator, so the astronaut, can interact to a more human-friendly level. So if the system can see a scene and can describe as a scene that was not previously known by the remote operators, and say, okay, I have a crater area in front of me with two big stones that could be dangerous for navigation, and one stone that could be interesting for scientific purposes. And then this is way more understandable to the end user, and vice versa. So the astronaut could also inform the robot on a task level to do what without needing an extreme precise metric knowledge of how the scene is set. All right, I think I talked too much. Thank you very much for the attention. And yeah.
So if you have any questions, yeah, we can have time for a couple of questions, I guess.
I actually have one quick question. You briefly mentioned issues with lighting. Can you maybe expand on what those issues were and maybe some workarounds that you either think can be deployed or maybe some that you already applied during those field tests? Thank you.
I mean, lighting conditions were not the reason for any subsystem, let's say, failing per se. So they were not as extreme as in the real in a real space environment. But they, especially during the day, they made the appearance of the environment change quite a lot because of the arrangement of shadows. I mean, the biggest one was again with the robot seeing itself in its casted shadows. I mean, of course, a lot of outlier rejection in that case if you have some prior, but nothing per se tackling the real issue at hand. That's why we want to move into multi-modality, so using some range sensing and being able to, for instance, segment different parts of the environment and say, okay, this is a cluster of stone that has a specific arrangement and so on. This you can do even without, let's say, really precise on the pixel level, say, visual information. So more of the, let's say, semantic understanding.
Okay, thank you again.